A couple of things. Just want to remind you guys, right now I'm passing out a copy of the homework set. As you well know, we're finishing up the last part of Chapter 5 today, and we're getting into 5.5. But so just to kind of remind you guys, your test 4 will be on Wednesday, April the 10th, which means your homework number 4, and here's a copy of it. You can click on this thing and actually print a copy of this thing. It will actually pop right up here as a PDF here. And that's the same thing that I'm passing out to you guys. It is due on Monday, so got a big homework over the weekend here. Also want to remind you guys of our review session today. We have a review session every Friday from 12:30 to 1:45 in Fretwell 113. And we will be going over any kind of questions you guys want to do. Just another reminder of other things you got to have due. So if we come over here to our Hawk system, I went ahead and signed in. We've got our quiz number 9 due. That is due on Saturday. You also have the lesson homeworks from section 5.2 and 5.3 due on Sunday. By all this stuff is due what? 11:59 or whatever the last possible second of Sunday is there. Does that make sense though? So you got lots of stuff to do and big calculus weekend here. So, and on Monday, I will go over this particular review set with you guys and get you prepared for the test. This is a good example. Of course, the test is going to be a lot shorter than this thing because, I put on this particular one, if you look at it, I put, what was it, 17? Yeah, 17 multiple choice questions. And then I put basically 5 free response questions, but you take a look at the first guy. We're back to doing derivatives again. So what I want to see here is basically the, you don't have to clean it up, but you just basically take the derivative of these guys and just write them down here and don't forget to label it. We're back to taking derivative of functions again. There's classic logs and exponentials. So speaking of that, let's go through the rules that you have to have memorized. And I keep drilling this into your head. Now, you got your basic rules, you know, derivative of x to the n and derivative of constants and all that other good stuff. But you also have the product rule, chain rule, and quotient rule on this stuff, okay? But with this, you also have the log and exponential rules. So again, just write them down, get them in your notes. But I added 2 more last time, just to let you guys know. And actually, every time I add one, you also have the rule of the chain rule version. So these are your new derivative rules. So number 1, if y equals the natural log of x, what's the derivative of the natural log of x? 1 over x. And number 2, the chain rule version of that. If you got y equals the natural log of a function, then y prime is going to be 1 over the function times the derivative function. And when you clean that up for the Hawks thing, putting it into their system, it's the derivative of the function divided by the function is what the derivative of the natural log of a function really is when you clean them up. Now there's your logs. Number 3, your exponentials. Y equals e to the x. What's the derivative of e to the x? It's the easiest thing you can remember. It's e to the x. It's the same thing. But then you got the chain rule version of that. So if you got y equals to anything other than x or t, whatever the independent variable is, if y equals e to a function, then y prime equals e to the function times the derivative of the exponent. Now, rule number 5. What if we happen to have an exponential that wasn't that famous base e, 2.71828, yada, yada, yada. If we don't have a base e and you have another base, like I put on your homework set, 7 to the x or something like that, if you got y equals a to the x, the derivative of that's going to be a to the x, because it is exponential, so you get the same thing back again, but times the adjusting factor, the natural log of the original base. And they've got a chain rule version of that guy. If you've got y equals a to a function, 7 raised to the x squared plus 3x minus 2 or something or other, then y prime is going to be the same thing, a raised to that function, 7 raised to the x squared plus 3x minus 2, whatever, but then chain rule times the derivative of the exponent, 2x minus 3, but then you got to also do times the natural log of a for having the adjusting factor for not having an e in the problem. And then the last 2. Number 7. Natural log is not the only logarithm out there. The traditional log is log base A. You've got the common log, that's called log base 10, but you also have log base 2, log base 3. You can have log base any positive number, not one's not very exciting, but any other base, a positive number base. So we call that y equals the log base A of x. It's still a log. And the derivative of the log, the natural log, is 1 over x, but then with not having the base e to get that natural log, you've got to have an adjusting factor. So the derivative of the log base a of x is going to be y prime equals 1 over x, but then the adjusting factor is going to be times 1 over the natural log of x. So with logs, you have the adjusting factor of 1 over the natural log of x. Okay? And then rule number 8. If you got y equals the log base a of a function, then my derivative is going to be, and today's a log, so derivative of a log is going to be 1 over the function, chain rule version of it, times the derivative of the inside, but then you got to do times that adjusting factor of 1 over the natural log of a. So these are your 8 formulas written out in all of its glory that you guys are expected to have memorized. Okay? Now, last time, to pick up with our notes and stuff like that, we were working on applications. In terms of applications and formulas, the real formulas you need to know is exponential growth and decay, and they work off a pattern of y equals c e to the kx, or t if you will. If you want to put it in terms of time, I'll put a t in there instead of an x. This is your exponential growth formula because k is positive. This would be a growth. Things that grow is like money when you invest it. Okay, we're not talking stock market where it's a gamble. We're talking about putting money in your bank at that low interest rate, but at least you're getting a constant interest rate, so you're not losing any money here. So that's a growth problem. And if it's a decay problem, like, for example, radioactive material or certain populations of communities are dwindling away, look at the formula. It's y equals c e to the negative kt. Same form, except the exponent's going to be negative. That c up front is going to be an initial amount that you start out with, and k is your either growth or decay rate. That could decay constant. Typically, it's a percentage or rate. It comes directly off of the old PERT formula. All right, so these are the big forms you need to know in terms of any kind of questions we give you guys. So, and we did do one other little problem here. So if you ever give you this, the limited growth formula is y equals c times 1 minus e to the negative kt, close parentheses there, where c and k are positive, so this would be a negative thing here. And when you look at this limited growth, pretty much what you get here is this thing is going to look something like this. It's an upside down exponential because it's negative, so but it looks like this. And there's this c value right here that as time goes on, it gets very, very close to, but doesn't go above. That's that limited growth. At most it's going to be able to grow is that sea level and stuff. So, all right. So we did a bunch of problems last time. We also talked about half-life. The definition of half-life is the amount of time it takes for an initial substance to be cut in half, whatever that initial substance is. So, and then these were the derivative of the exponential and exponential to a function not base e, but base b. And these were the derivative forms of the log base b, whether you got x or a function of it that we just went over. So pick up where we left off last time. We picked up right here with the radioactive decay problem here. Okay? So it says this. The decay rate for a radioactive isotope is 5.8% per year. Find the half-life of the isotope. Now, again, we were just talking about this. What is half-life? Half-life is the amount of time it takes for an initial amount to decay to half the initial amount. Definition of half-life. The amount of time it takes for an initial amount of whatever, carbon-14 or plutonium, whatever you're playing with. It takes the half-life is whatever you start out with, the amount of time it takes for it to decay in half, because radioactive material will decay on you. So the decay rate for radioactive isotope is 5.8%. So this is my K. It is 5.8%. That's my percentage, and that would be 0.058. And in terms of radioactive growth or decay, it's the formula. A equals C e to the negative KT, because it is a decay problem. And this is the K value here. So I get A is equal to C e to the negative 0.058 T. Now, when they ask for half-life, the question is, what's the time? How long is it going to take? But here's my problem. They didn't give me any other information. And let me explain why. They didn't have to. Well, I need to know what C and A are. Well, let me tell you what C and A. C is the initial amount that you're starting out with. They didn't give you C. It's all right. So you can actually make up a number for that if you want to. How much of plutonium would you like to start out with? 1? All right, let's go with 1,000 kilograms. Okay? Look at the number we can have. But you can use 1 if you want to. But let's go with 1,000. I want to see the numbers in this. 1,000 kilograms. Now, if you've got 1,000 kilograms of plutonium, I'm sure the North Koreans would like to talk to you. So, but you got a nice amount of plutonium right here, right? Now, it's going to be cut in half. And the question is, how long will it take for, what would the amount back be? If you start out with 1,000, and we're talking about half-life, it's the amount of time it takes for that initial substance to be cut in half. So what's half of 1,000? 500 kilograms. And you could have started out with 1 kilogram, then it would have been a half a kilogram. That would have been the exact same thing. And so, when you plug these numbers in here, you'll see why the constants won't matter. The amount that you're going to get back is going to be 500. When you start out with 1,000, e to the negative 0.058 t. So this is the initial amount and the amount. So officially, I could have just started with C, but the amount after time would have been half C, because let me show you what's going to happen here. You got to solve for T. Where's T located at? It's in the exponent of an E. You got to get that E term by himself. So what's your first move? What's always your first move? You want to divide. Get the E term by himself. Isolate your victim. Divide by 1,000. And when you take that 500 and divide by 1,000, what do you get? 1/2, the half-life. And that's what I'm saying. If this A was a half C, and this was just C, and you divide by C, the C's cancel, and the half will show up. E to the negative 0.058 t. Now, what's your next move? What kills off an E? Natural log. So you can take the natural log of both sides. What I did one side or the other. And E and natural log cancels. This leaves me with the natural log of 1/2 is equal to, and your exponent pops out in front, negative 0.058 t. What's your last move? Get the t by himself. I'm going to divide by negative 0.058. Divide by negative 0.058. This gives me t is equal to, and I go grab my handy dandy calculator here, and I'm going to put this on my calculator. So this is the natural log of 1/2 divided by negative 0.058. Does that make sense? And I end up getting t to be 11.95081346. What is time measured in? Years. But they did say round it to the nearest tenth of a year. Please do that. Round it to a nearest tenth of a year. Your answer is 11.95. Round it off. So t is equal to 11.95, but they said 1/10 of a year. So go to the 10th spot and look behind it. What do you see? 5. So you got to round up. You're rounding a 9 up to, next one will be a 0. So the next thing, actually, the answer is going to be what? 12.0, because you want to specify the fact that they wanted a tenth of it, round it to the nearest tenth. So put the 0.0 in there, years. So yeah, you're right. It's going to take you 12 years for your plutonium or whatever radioactive isotope you're playing with these kind of numbers to literally be cut in half. Does that make sense? All right, let's take a look at the next guy. Next one says this. The amount of goods and services that cost $200 on January 1st, 1996 cost $299.36 on January 1st, 2005. Estimate the cost of the sample goods and services on January 2010, January 1st, 2010, assuming the cost is growing exponentially. And round your answer off to the nearest cent. So we got, and it's kind of like life, prices of things are going up, okay? And they're going up exponentially. So talk to your grandparents and ask them, how much did the Coke cost back in the 1940s? Well, a nickel, okay. What's it cost now? $1.25. It's kind of sad. So things are growing exponentially, you understand? So when we're looking at it from our initial amount, this is my C. And we're going to measure this from January 1st, 1996. All right? This thing, this would be my initial amount. And the initial amount was my cost was, and this is my C, would be $200. Does that make sense? And so they said exponential, grow exponentially. My formula is A or Y equals C e to the KT. But here K is going to be positive. And they didn't give me K, so I'm going to have to go find it. But I know what C is. C is the initial amount, and that goes here. So A is equal to 200 e to the KT, and we're measuring from 1996. But then they tell me this, more information. On January 1st, 2005, we have a cost of $299.36. How many years is this? Time is measured in years. What is my time? I'm going from January 1st, 1996 to 2005. 9 years. T equals 9. Does that make sense? 9 years. From pretty much 1996 to 2005. Does that make sense? 9 years. So in 9 years, so this is going to be my time. So 200 e to the k times 9 is equal to $299.36. Does that make sense? What's left? There's only one thing you can solve for when you got the initial amount and a little bit later another amount, and that is you got to solve for k. Only variable left. How are you going to solve for k? What's your first move? I'm going to divide by 200. Get that e by himself. So this is 299.36 divided by 200 is equal to, this will cancel, e to the 9k. What's your next move? What gets rid of that e? Natural log. Take the natural log of both sides. Natural log and e's cancel. This leaves you with the natural log of 299.36 divided by 200 is equal to 9k. What's your last move? Divided by 9. And I want you to see something in here. Because I was looking at a bunch of you guys in the classroom, and you already got your calculator just a bunching away on this thing, and also, I haven't touched my calculator yet. I don't touch the calculator. I mean, I'm leaving it just like this. I'm going to type this whole thing. I'll show you when I use my calculator. I'm manipulating the equation first, and only at the end will I actually just go ahead and put this thing on a calculator to get me this k. So, here we go. It's going to be the natural log of 299.36 divided by 200, and close parentheses for that natural log, and then we're taking that and dividing it by 9. Notice how I typed it in on my T84. Okay? And I get k to be equal to 0.04481438884. They didn't specify anything in terms of rounding off k. So, don't round off anything until the final answer. I'm going to use this value as k. It's only digits, and I'm using my calculator, No need to round it up. I know, then we'll round it off to the nearest cent. This isn't money, this is your K. We haven't answered the question yet. This just allowed me to actually get the modeling equation. Now knowing what K is, here we go. A is equal to 200 e to the K, which we now know is 0.044814388 T. Put my K up there. Does that make sense? Now, answer the question. The question is, estimate the cost of goods and services on January 1st, year of our Lord 2010. Now, remember when we started this thing? We started it in 1999, right? January 1st, 1996, excuse me. January 1st, 1996. We went to January 1st, 2005, which was 9 years, and now January 1st, 1996 to January 1st, 2010. How many years is that? How many? 14 years. Does that make sense? Did I lose you guys anywhere? Okay, so 14 years. Now I'm going to plug 14 into this guy, and I get A is equal to 200 e to the 0.044814388 times 14. And now, back to putting it on my calculator. 200 e raised to the 0.044814388, no rounding, times 14 years. And that gives me how much? And they said round it to the nearest penny, so I got 374.547565. Now, remember, on halts as well as tests, pay attention to how they want you to put in the answer, because if you type in the answer wrong, they're not going to be happy with you guys. They said to the nearest penny, because this is money. So to the nearest penny is at the 100 spot right here. And because of that 7 right there, I'm going to round up. What is my answer for the amount it's going to cost us now? $374.55. So, yep, here it is. What used to cost $200 in 1996 now costs us $374.55 today. Does that make sense? Did I lose you guys anyway? Questions? All right. The demand for oil in a particular country doubles every 4 years. How long will it take for demand to triple? Round your answer to the nearest hundredth of a year, okay? So again, what we have here is oil, and if it doubles every 4 years, you're having that exponential growth. Does that make sense? So with that exponential growth, here it is. I have this. A couple of different ways you can go about doing this thing, but I'm going to use it this way. Y equals C e to the k t. Okay? That first part of the puzzle is basically for you to figure out what k is. So it doubles every 4 years. So it doesn't matter what the price of it is, wait 4 years and it's going to double, right? So if C is the amount of oil now, what will it be in 4 years? In 4 years, what will the amount be then? Amount would be equal to what? It doubles 2 times C. Does that make sense? So if you want to, give yourself the price of oil, $50 a barrel, whatever, okay? Then if it doubles every 4 years, what's it going to be? $100 a barrel. Does that make sense? But it doesn't matter what it is because you can plug this in. This will be C e to the k. If I plug in time as 4, I will get 2c. And I want you to solve for k. I know you got 2 different variables here, but I just want to show you what happens when I actually don't put a number in for that c. What's the first move when you want to solve for k? K is in the exponent. What's your first move to get the e to that exponent by himself? You're going to divide by c. And when you divide by c, it ends up canceling all over the place. And it goes away. So it leaves you with 2 is equal to e to the 4k. What's your next move? Got to get the e by himself. That's your natural log. Okay? So you end up with natural log and e cancels. So that leaves you with the natural log of 2 equals 4k. And then I'm going to divide by 4. And then that's when I go grab my calculator and put it on there. This would be, quote, the natural log of 2 divided by 4. Natural log of 2, close parentheses, divided by 4. I end up getting 0.173286795.1. And I don't round these decimals until the final answer. So that's my k value. Basically, it's growing at the old 17.3% per year type thing here. Okay? So my formula now is going to be y equals CE to the 0.173286795.1t. What's the question? How long? It's a question of time. Will it take for the demand to triple? To triple, the amount that you want to get back will be 3 times C. Whatever the price of that oil is, it's going to triple to 3 times that original cost. Does that make sense? So I'm going to plug in for that y, or the amount 3C is equal to CE to the 0.173286795.1t. What's my first move to solve for t? I know that c's bothering you, but don't, because your first move is always to do what? Divide, and when you divide, what happens to the c's? They're going to cancel, and you're left with 3 is equal to e to the 0.173286795.1t. Now, what kills off that e? Natural log. Take the natural log of both sides. That cancels. You're left with, bring it down this way, the natural log of 3 equals 0.173286795.1t. And the last move you got to have is to do what? Get the t by himself. Divide. 0.173286795.1 on both sides. 86795.1. And so I'm going to stick this on my calculator. It is the natural log of 3 divided by 0.173286795.1 is, I got t to be equal to 6.33985 years. And that's this one I didn't write all the decimals out because what do they want me to do? They wanted me to round this thing to the nearest hundredth of a year. Does that make sense? And the nearest hundredth of a year, this is tenths, hundredths, thousandths, hundreds. What is a 9 going to do to my rounding? I'm going to round it up. So the answer is what? 6.34 years. That is the answer. So it's going to triple in 6.34 years if the trend continues. Does that make sense? Take a look at the next guy. Determine the value of a piece of machinery that declines exponentially. Declines exponentially is a fancy way of saying an exponential decay. A machine that is purchased 4 years ago for $70,000 is worth $34,000 today. What will the value of the machine be 4 years from now? Okay, round it to the nearest penny. This is called depreciation. And as you well know, when you actually run a company or something or other, you're going to have to pay taxes on everything. That's just the way things are. When you talk about your company, you got to pay taxes on the stuff that you didn't sell because it's still sitting on your shop. Just when you have these just before tax season, these end of year sales and all this other good stuff. But when it comes to down to paying taxes on your property, you got to figure out what the property is worth. Property taxes. But if they are, something new costs a lot. Something that's a little older doesn't cost quite as much because of that depreciation. That's what we want to find in this problem. What's our depreciation? What's it cost right now? So this is depreciation, but it's still exponentially decaying. So you got the formula y or a equals c e to the kt, but being decaying exponentially, this K is gonna have to be negative. Does that make sense? So I know this is my model here. All right, so initially, we're talking about 4 years ago, so this is gonna be time equals 0. What did this thing cost? $70,000. Does that make sense? And that's my initial amount. That's going to be my C value. So I get Y equals CE to the negative KT turns into 70,000 E to the negative KT. So this is my formula, plugging in for C. Now, then, 4 years, in 4 years, so time equals 4, what does the thing cost now in 4 years? $34,000. So this will end up being my A or my Y, whatever letter you want to call that thing there. This is my Y, $34,000. So when I plug in time is 4, so as Y equals 70,000 E to the negative KT, I plug in Y, and the time is 4, the Y is going to be 34,000 equals 70,000 E to the negative K times your time is 4. When you plug, this is the initial amount, so that just tells you the C. When you plug in the next value, the thing you need to solve for is the decay rate. Solve for K. So my first move, of course, is divide by 70,000. Got your pattern on that. This cancels. That leaves me with 34,000 over 70,000 equals E to the negative 4K. What's your next move? Then you got the E by himself. What are you going to do? Take the natural log of both sides, and the natural log of E cancel. That leaves you with the natural log of 34,000 over 70,000 equals negative 4K. What's your next move? Solve for K, divide by negative 4. And you get K to be equal to, putting this on my calculator, natural log of 34,000 divided by 70,000, close parentheses, divided by negative 4. And end up getting 0.1805336794. And again, I'm a big fan of no rounding, not until the final answer. It gives you more accurate answers. Okay? So now that I've got my K, that button put on, therefore my formula, A or Y, is equal to C, which was $70,000 E to the negative. I know K is, it's 0.1805336794T. This is my modeling equation. Now, what's the question? You got to kind of implicitly understand the numbers here. What will the value be 4 years from now? Now, we started at time equals 0. In 4 years, which is a quote unquote, this is now time equals 4, the way I initialized this. Does that make sense? So 4 years from now would be time equals what? From since how old is this machine basically? 4 years, it was $34,000. That was at this, and now this is our now time. We want 4 more years. What would time be then? 8. So the question is, time equals 8, which is 4 years from now. Okay, this is when it was new. We estimated after 4 years, which is right now, it's $34,000. 4 more years, which would be time equals 8. What would the cost be? So all I got to do now is just plug in 8 for time. So Y would be equal to 70,000 E to the negative 0.180533679 times 8. And I'll stick that on my calculator. 70,000 times E raised to the negative 0.180533679 times your time, which was 8 years. And I end up getting, how much is it worth now that we have to report to our taxes? Y equals 16,514.28571. And I wrote down all the decimals for you guys because I want to make sure that you follow directions. What did it say round it to? To the nearest cent, because this is money. So that's the nearest 100 spot. So I got 0.285, and that 5 is going to round it up. Does that make sense? So my answer here is the amount is going to be $16,514.28571. $0.29 is the value. Did I lose you anywhere? Does that make sense? Okay? One more, and we'll move on to chapter 6.1, which is not on the test, but ain't no time like the present to learn something, brother. Bones from the skeleton of a prehistoric creature has lost 65% of their carbon-14. Note that carbon-14 has a constant of proportionality, which is approximately K equals 0.000124. Carbon-14 goes down kind of slow. Yeah. Yeah, 5.5b we omit. We talked about that. We end the test with 5.5a. So 5.5b is not going to be on the test because it's something that we were ordered to not cover. It's okay. All right, so talk about that in a second. So estimate the age of the bones to the nearest tenth of a year. So this carbon-14 is again an exponential decay. So my formula is going to be y or a is equal to CE to the negative KT because the carbon-14 decays. They gave me the K value. Well, that was awfully nice of them. So y equals CE to the negative 0.0000124T. Now, here's the deal. Again, interpreting this stuff. The bones of a skeleton of a prehistoric creature has lost 65%. Now, this is words we're going to have to play with here. It has lost 65% of the C14, the carbon-14 stuff. Okay? If you lost 65%, so the initial amount, we're going to do this stuff again. The initial amount of C14, we're going to call this C. I don't know how much bone has of carbon-14. I have actually no idea, but they've told me that it's lost 65%. Pay attention to that. They're throwing a curveball at you guys. If you lose 65%, what is actually the amount left of your C14? What is it? Try again. 35, even better. Now, 100% is everything. 100% of carbon-14 is all you got. If you lost 65%, what's left? 35% of the initial amount. Does that make sense? And the initial amount we're going to say is C. So putting, remember, percentage for people who can't do math, this will be 0.35 times C, C being the initial amount of carbon-14. So this is the amount left, okay? And they want to know, quote, how old it is. So let's go find out. So A, which is your Y, is 0.35C is equal to CE to the negative 0.0000124T. Now, here's your equation. C is the initial amount, which is arbitrary, because they told me about the percentages. But the main thing is, they went around to the nearest tenth of a year. We're solving for time. Time is the question. So what's my first move? Well, the t is in the exponent of an e, so I got to get the e term by himself. So what's my first move? Divide by c. This cancels. That leaves me with 0.35 is equal to e to the negative 0.0000124t. What's your next move? Natural log both sides. And the natural log and e will cancel. This leaves you with the natural log of 0.35 is equal to negative 0.000301224t. And then the last thing I got to do is divide. Negative 0.0000124. This cancels. And I'm left with t equals, and again, sticking on the old handy-dandy calculator, natural log of 0.35, close parentheses there, divided by the negative 0.0000124, and end up getting 8,466.307456. And then, so here's my t value, but they wanted me to round it to the nearest tenth. So what is my answer here? T is equal to 8,466.3 what? Years. 8,466 years old approximately. Does that make sense? Don't lose you guys anywhere. Notice how they do that percentage, because that's a curveball. Everybody wants to use the 0.65, but that's how much it lost. You got to figure out how much is still left over. Does that make sense? Now, as we were just mentioning this, there is that section 5.5b on logarithmic differentiation, elasticity, and demand. This, we were told, it's not going to be on your test, so or the exam, so we're not going to be covering this particular material. It's more basically elasticity and more taking derivative of those log equations and stuff, but we're not going to admit that, which means we're done with chapter 5. So we're going to move on, and so a lot of people ask me, you know, well, how should I prepare for this test? Well, number one, I've just given you guys a nice big homework set here, so I think Sandus is still passing them out there. Another thing to do is make sure you know how to answer these kind of questions and stuff like that. So if you work on the review set, because we do put these review sets in your notebook packet here, if you're not sure that you got something right or something or other, come by and see me. See me after class. I got the solutions up here, but I want you to try them first. I don't give you the solutions until you try it first. So, all right. So, but now we're moving on into chapter 6. Chapter 6 is the last chapter we're covering. And chapter 6 is about something called the integral. Now, the integral idea is very simple. It is antiderivative. So let's think about this for a second. Since day one in this class, we pretty much have been giving you guys a function, and we ask about f prime of x, the derivative. Right? We give you f of x, which is the function, and we ask you about what's the derivative. That's what we've done. But, so we give you a function, we ask you about a derivative. What if we do this in reverse? In reverse, what we do is we're going to give you f prime of x, we're going to give you the derivative, and then we're going to ask about what is f of x. We're going to give you the rate of change function. And then we're going to turn around and ask you about what was the original function. Well, you remember all those derivative rules? I hope so, because there's like a huge amount of your test, the final exam is going to be on it. What was your basic rule? Derivative of constant was 0. Derivative of x to the n was n x to the n minus 1. Okay? Well, if there's rules for taking the derivative, guess what? There's rules for taking the antiderivative, and that's what this is called. This is called the antiderivative. And an antiderivative is the same thing as what we call integration. So when you hear the word integrate or integration, that means antiderivative. And here we have a special notation for that. The notation for that is this. Here's your idea. This elongated s means antiderivative or integral. The integral of f prime of x dx. Dx is just telling you what the variable is. So the integral of the derivative function will actually give you the original function back. Here's your problem. Plus c. C is called this constant integration, because here's my problem. We're talking about in reverse. So what we're saying here is this. The derivative of what is 2x? What do I need to take derivative of is 2x? Think about it. What do I need? X squared. The derivative of x squared is 2x, right? So we'll give you 2x. The antiderivative of 2x is x squared. What's the derivative of 5? 0. So the antiderivative of 0 is 5. Well, what if I gave you 7? What's the derivative of 7? 0. Therefore, the antiderivative of 0 is 7. Well, no, it can't be 5 and 7 at the same time. The problem is when you integrate a constant, take an antiderivative of 0, you end up getting what we call a plus c. It's going to be an arbitrary constant. I don't know if it's 5 or 7 or whatever. I'll have to go investigate. We'll give you some numbers on that. So this is called the constant integration for the ability to integrate 0. The integral of 0 is always an arbitrary constant. So, these are antiderivative. We're going in reverse. And this is your main idea here. You take the integral of the antiderivative, it gives you the original function back up to a constant plus c. So here are the basic rules you're going to need to know. More rules. The integral, I'm going to call k a constant, dx. K is a constant. Integral of a constant is going to be a constant times x plus c. And if you ever get in trouble, just do it in reverse. The integral of 5 with respect to x is 5x plus c. All right, so what's the root of 5x? 5. It'll be what's inside your bracket, in between the integral and the d thing here. Okay? The integral of a constant times a function, dx. Well, with derivatives, what do constants do? They hold over. With integrals, antiderivatives, constants hold over. Constant goes out front. So this will be the constant times integral of f of x dx. Constants, just pull them out front. You're going to be focusing on the variable. Here comes your big one. It's called the power rule. The integral of x to the n dx. What's the integral of x to the n dx? Well, when you took a derivative, the rule was you put the exponent out front and you subtracted one, right? We're working it in reverse. What's the opposite of subtracting one from an exponent? Adding one to an exponent. But in the opposite of sticking it in front is stick it in the denominator. So the rule is going to be x to the n plus 1 over n plus 1. And then you always have this arbitrary plus c, because you could have also plus 0, and integral of 0 is a constant. So an example of this would be, what is the integral of x cubed dx? The integral, you add 1 over add 1. So n is 3. Add 1 to 3, what do you get? X to the 4th over 4 plus c. And if you don't believe me, okay, look at x to the 4th over 4. That's the same thing as 1/4 x to the 4th. The derivative of x to the 4th, you bring down the 4. But 4 times a 4th, it cancels. You get 1. X and subtract 1, 3. You get x cubed back again. It's the rules in reverse. Okay? And this applies provided n does not equal -1. The reason why n doesn't equal -1 is we have a special rule for that one. The integral of x to the -1 dx is the same thing as the integral of 1 over x dx. Now think about it. What function out there that you took the derivative of actually gave you 1 over x? Derivative, what function is 1 over x? Natural log of officially absolute value of x. Let's see, because you can't take the natural log of a negative number. So always do absolute values on that to remind you of that. Other rules you need to know. What do you think the integral of e to the x dx is going to be? The derivative of e to the x is e to the x. What do you think the antiderivative of e to the x is going to be? That gives that the other way too. E to the x plus c. Okay. These are the basic rules right here that you guys need to know. And one more, and I'll put him down here, it's called the sum difference rule. When you integrate a function f of x plus or minus another function g of x dx, you're going to integrate the first function plus or minus, you're going to integrate the second function dx. Now, I've written all these rules with the famous dx on it, because x is usually my famous variable. However, remember this. The integral of f prime of t dt, t is the variable. This is going to give you f of t plus c. You don't always have to have an x. T represents time. Maybe you want to integrate with the variable time instead of x representing some commodity or whatever. Okay? So this is where we're headed to in Chapter 6. Chapter 6, the applications of the integrals. We'll go through these, but if you turn over the page real quick, you're going to see us integrate a bunch of problems. And look at the notation here. But you guys remember what I taught you guys about the first set of taking the derivatives of these problems? First thing you got to do is what? Clean it up. Same rule applies here. I don't have a rule for integrating this thing, but algebraically I can divide each term by this x to the 4th, clean it up, and then I can integrate each one. We'll do that after the test. So study hard. See you guys then.